Okay, we discussed the idea of content-based, and at the end we summarized all pros and cons, and we came up with this last observation that motivates the introduction of this new technique, named collaborative filtering. So the idea that in content-based filtering, basically, we are not going to exploit anyway all the rankings provided by the other users about the products. So the question is to what extent we can use this. But before of that, I want to show you a very nice blog. I would. Okay. So what is nice is in this blog is that the author basically analyzed 80 millions of Amazon product review, coming up with a lot of statistics about those items. And what is interesting here is that we have the distribution of ratings. So you know that in Amazon, as an example, we have a rating between actually 0 and 5, I think. You can give also 0, I'm not sure. Anyway, 1 and 5. And so this is the number of products that get that evaluation. And this is also a confirmation about one of the arguments we discussed, that most likely people is going to leave positive evaluation rather than negative ones, which does not mean that all the products are very good. It means simply that most of the time people that does not like a product is not going to leave a message, to leave a ranking. So my suggestion is to have a look to this blog to have a rough understanding on the context we are moving on. And it's also very nice because basically you have, if I'm not wrong, 1 second, the average rating for category. And so again, those are the kind of details that can make the difference in recommendation system. So we will see later on that there are some kind of average when we will talk in the last part on latent factors and how to put together all the technique we saw. But you see that digital music, usually the average is very high, while if you go to cell phone and accessories, the average is relatively low, or at least there is a significant difference between the two. Okay? So have a look to this in order to better understand the context we are discussing. Okay, so what is the idea behind collaborative filtering? The idea is to leverage this rich information about the ratings of the other users in order to provide recommendations and to possibly provide the recommendation with a better quality. Okay? So the main architecture, the concept is relatively simple. Again, we have a user X. We want to find a set N of other users that are similar to our user X. So this is one of the main problems. How can we establish the similarity between two users? Okay? So we have a user, we have other guys. We want to find similar users in terms of what? In terms of preferences. So the idea is to analyze the ratings of the user and of the set n in order to, and of the other users in order to find out the set n of similar users. So we have to define very clearly what we do mean by similarity. And once we have those users, we can possibly suggest, recommend items that those guys likes and have not yet seen by X. Okay? So now we have user in place, and we have also rating in place, because the ratings are the tools we use in order to establish the similarity between the users. Good. So completely different setting with respect to what we saw before. And so what we want to do, basically, we want to estimate the X ratings basing on the ratings of the user n. Okay. Good. First exploration. In the picture before, we discussed the fact that the key ingredient here is to find out similar users. Okay, and we can explore a number of alternatives that most likely will become even more clear in the next slides, in which we have an example. But let's start to discuss at least the idea. Okay, the first alternative is the Jacquard similarity. I remind you that the Jacquard similarity is something we use in order to evaluate the similarity of two sets. Where did we see the Jacquard similarity? In order to evaluate the quality of a search engine. Okay, we can use the Jacquard similarity on top k elements in order to evaluate the quality of a search engine. Okay, good. The main problem here is that it ignores. Okay, you have two set of items, but it completely ignores the ratings of those items. It simply observes what items are in both the sets, okay? But does not consider what are the ratings of those items. So since we say that our main idea is to exploit the value of the rating of the other arguments, Jacquard similarity seems to do not work properly in this particular case. Okay, okay, so we can come up with the usual technique with cosine similarity. Cosine similarity seems to work pretty well, and indeed we used it already before to establish the connection between products and user profiles. So it seems a good option. There is a main problem here, is that what is the main problem of the utility matrix? Okay, we have basically two main problems, that we have unknown values. Okay, so if when we have unknown values, we put a 0 in order to compute the cosine similarity, the fact is that actually we are to some extent biasing the computation of the cosine similarity to the lower value of our ranking between 0 and 5. Okay? Does this make sense? We have a sparse matrix. But if we want to compute the cosine similarity between two vectors, we have to fill up the unknown elements of the sparse matrix with something. Okay? Putting 0 seems to be a quite natural idea. It is. The problem is that 0 is anyway a valid value for our ratings. So basically we are to some extent biasing our cosine computation toward the 0. So we are considering the missing rating as negative. I remind you that we have value between 0 and 5. 0 means negative, 5 means absolutely positive, and roughly 3 is the average. Okay? So apparently there is a problem also with the cosine similarity. So we can exploit basically another concept, the so-called Pearson coefficient, correlation coefficient, which is also called the centered cosine similarity. Okay, the idea is that since we have a problem with the 0 in the cosine similarity, what we can do is we can normalize the vectors in order to avoid this problem. And let's make an example to make it clear. But the idea of the normalization is basically is that we subtract the average, okay, in order to bring the ratings instead from 0 to 5, okay, to be centered in the average. So it's not anymore 3 the average value, but it's 0 now. Okay? Since it's 0, and thus I will also support negative values, now we can apply the cosine similarity without this problem. But let's make it clear by an example. Okay? Good. Again, don't forget what is our purpose. Our purpose here is to identify a set of n neighbors of the X user we want to provide a recommendation to. And this set of X neighbors must be computed according to the similarity of the considered user, namely X, and all the elements, the users in the set. Okay, this is our purpose. Good. Okay, this is a possible utility matrix in which we have user A, B, C, and D. And then we have Harry Potter 1, Harry Potter 2, Harry Potter 3, Star Wars 1, Star Wars 2, Star Wars 3, and so on and so forth. Okay? This is the utility matrix. As expected, is a sparse matrix. Namely, we have a number of empty cells. And we want to capture this idea. Let's have a look to A and B, and then to A and C. Okay. Why A and B, even if we look at that very roughly, very intuitively to this matrix, should be considered most similar than A and C? What is your guess? Sorry, yeah.
The ranks of A are very different to the
True, but let me add something. Okay, main observation. We want to provide suggestion on the basis of the fact that both users like something. Not on the fact that both users dislike something. We are not going to provide recommendation on something you don't like. We are going to provide recommendation on something you like. And in order to provide those recommendations, I need to find similar users. So people that like stuff similarly to you. Okay, does this help a bit more? Okay, let's focus on Harry Potter 1. A and B both loves it. Okay, B loves it a bit more, but also A loves it. Good. We don't know anything about C, so we cannot claim anything about C. But let's see now the other movies that have been evaluated by both. Now, if we focus on Star Wars 1 and in TW, sorry, I don't remember the name of this movie. What? Twilights. I think it's Twilights. Okay, good. And Twilights. So what you can see is that user A likes Twilights, which user C dislike, and on the contrary, user A likes user C likes Star Wars that user A dislikes. Okay, so even if we have, to some extent, more information about the tests of user A and C, because at least 2 movies are matching, namely, not matching, sorry, because we have the judgment, the rates of 2 movies, while in the case of A and C, we have only 1 movie that has been rated by both. What we can guess is that since that single movie has been rated by both positively, most likely those 2 users are similar than the other ones that have always a completely different rating of the movie. Okay, does this make sense? So that's why we want to capture this intuition that the similarity of A and B is greater than the similarity of A and C. Is this clear to everybody? Remember that we want to recommend items that are that people likes, not items that people does not like. Sorry. Okay. So good. Let's explore now the alternatives that we have considered. Okay, Jacquard. We have 1/5 about A and B, because why? We have 5 movies: Harry Potter 1, Harry Potter 2, Harry Potter 3, Twilight, and Star Wars, among which only 1 has been evaluated by both, so it's 1/5, while AC is 2/4, because we have Harry Potter 1, what is it? Twilight and Star Wars, right? Y/5. Two of them have been, okay, sorry, 1, 2, 3, 4, sorry. Is Harry Potter 1, Twilight, Star Wars 1, and Star Wars 2, the union set, while the intersection is only Twilight and Star Wars, so it's 2/4, okay? So we get, first of all, the intuition is not captured, but more importantly, in that case, we are not considering at all the ratings. We are simply considering the union of the sets and the intersection of the set, irrespectively from the evaluation of the user. So, does not work. If we apply the cosine similarity, actually it captures the idea, okay? Because indeed, in this particular case, we have 0.38 against 0.32, and actually it happens that 38 is bigger, so the similarity of AB is bigger than the similarity of AC. But, okay, it doesn't capture actually the fact that it's very different, those guys are very different, okay? So let's try to apply the cosine similarity subtracting the average, namely the Pearson coefficient. So what we have here is this matrix. We compute the average of the user. So in this particular case is 4 plus 1 plus 1 for the user A is 10, okay, divided by 3. And so we are going to subtract 4 minus 10/3, which is 12 minus 10/3, and so 2/3, okay? We are simply subtracting the average for each row. Is this clear? Not from the faces, actually. So let me, I will simply do the exercise for the first row. So we have 4, 5, 1, and this is HP1, so Harry Potter 1, Twilight, and Star Wars 1. So the sum is 10, the movies are 3, so this is the average, and so I will subtract the average. So it's 4 minus 10/3, which is 2/3. And so now instead of 4, I have 2 over 3, and similarly for all the others. Okay? So what we did now is that instead of considering 0 as a negative value, as in the cosine similarity, now 0 is the average, because if you sum up all the entry, okay, in line, you will get the 0 value. Seven over 3 minus 7 over 3. So now you will get 0 as the average. So we basically moved the average of the value. Instead of being between 0 and 5, now we have that the value for each row are centered in 0. Okay, and so I can apply now more conveniently the cosine similarity without being worried that we are actually biasing towards negative values. Does this make sense to everybody? Okay, so good. Now we have a different technique, and so if now we apply the cosine similarity with these values, we get that the similarity of A and B is 0.092, which is much bigger than the similarity of A and C, which is minus 0.559. And this also capture, because look, now we have a minus that according to our intuition, those users are going in completely different direction with respect to the values that we have. Okay? Good.
Sorry, shouldn't we put 0 in place of the missing items?
Yeah. You apply cosine similarity as before. But now 0 does not anymore mean.
Because there it says that considering missing ratings negative. I don't understand why.
No. It's not the cosine similarity. By the cosine similarity, if you apply the cosine similarity, so you put 0 in that metric, that zero now is considered as a negative evaluation.
Okay.
So we apply this, say it, trick in order now to center the values on 0 and to have both negative and positive value. Negative means, where is it here? Negative means negatively evaluated, something that you don't like. Okay? If you put 0 there, you are basically saying that you don't like. If you put 0 here, you're basically saying that it doesn't matter. It's a completely different message, right? So 0 there, it's I don't like. 0 here, it means it doesn't matter. And if you want to compute the similarity of something that you don't know, most likely you will say it doesn't matter rather than I don't like. Okay? Is this clear now? Good. What is nice by this person coefficient or center cosine is that not only allows us to deal with those negative values in the proper way, but also allow us to, since we are averaging by row, namely we are averaging by users, we also take into consideration the fact that there are very generous users that, will always give very positive ratings, and there are very, the so-called easy raters, or the so-called tough raters, guys that will never give you more than, it's exactly the same as it happens most of the time when somebody has to be evaluated, right? When you give a vote, it depends on the guy that is evaluating you. But since you are normalizing by row, you take into consideration these in order to provide a better evaluation. Okay? Good. So now we have a mechanism in order to understand the similarity between users. Okay, so we can select the set n, and so what we do is the following. If we have Rx, which is the vector of user X ratings. What we do is we are going to select this set of n users that are similar to X according to the ratings. So we apply exactly the person coefficient we saw before, and we apply the cosine similarity in order to check the similarity between users. And now we select the most, the top k among those users that have already provided a rating for the item I. Because here, what we want to evaluate is the rating of the user X about the item I. Okay? Clearly, X have never evaluated I. So what we want to do is we want to make this guess considering the value of the user in its neighborhood, in the neighborhood of X. Okay? So again, we have two basic ideas as similar to what we saw before in the content-based filtering. Either we make a simple average, so I get the average of each user, and I make the average of all the contribution. Or, since I have also a measure of the similarity, right? Is this clear? The cosine similarity is a measure of the similarity. It's not a Boolean vector. It tells also you how much those users are similar. And thus, I can weight the contribution of each rating of each user for the item I according to the similarity of this user to the considered one. Okay? And clearly, you can think about millions of alternatives. I mean, not millions, but a number of other alternatives, but this is the main concept. Okay, good. So let's recap very quickly. Okay, we have a user. What we want to do, we want to find similar user. We discussed all the alternatives. We came up with the person coefficient. This person coefficient allows us to find out a set n of similar users that have already provided a recommendation for an item that we want to recommend to the user. And thus, what we want to do is we can make, in order to guess the value of the rating of the user and then to guess to what extent that item is interesting for the user, we can compute an average, a weighted, average, considering the similarity among the users as the weight. And the ratings of the n of the users in the set n as the value to be weighted. Okay, good. Okay, so far we have considered the user-to-user collaborative filtering. Namely, the set n has been computed among similar users to the ones we are considering. But we can consider the completely dual approach, item to item. So instead of looking for similar user, we are looking for similar items. Okay? If a user likes, again, a given book, I'm looking for books that are similar to that one in order to provide him a recommendation. Okay? Okay. So basically, the idea is dual. Nothing new. For an item I, we find other similar items, and now we have a clear technique to do it. Instead of considering the by row as before, we consider it by columns. Nothing different. And so we estimate the rating for a given item I based on the rating for the similar items. Okay? Exactly a dual approach. And indeed, if now we want to estimate the rating of the user X for the item I, now what we do, now N is not anymore made of users, but is made of products, is made of items. So we are looking for similar items to the given one, to I. So J are items that are similar. And then we multiply it by the rating of the user for that similar items. Okay, it's absolutely a dual approach. Nothing changed. Now, clearly, Ij now are items. Okay. Rxj now are the rating of the user X, the ones that we are considering, on the other items, not on the ones that I want to suggest clearly. Okay? And N now, in this case, is a set not made of k users, but of k products. Okay? It's absolutely a dual approach. Let's see an example that hopefully will clarify everything. Questions? Okay, good. So, this is our utility matrix. And you see we have a number of movies, a number of users. In some cases, in our utility matrix, we have the ratings. So, as an example, this means that the user 3 likes the movie 6, 3. This means that the user 5 likes the movie 3, 2, and so on and so forth. So you have ratings between 1 and 5. And that's it. What do we want to do now? What is the main purpose here of a recommending system? Wake up. Yes, but before recommending, you have to guess what is the value of unknown ratings. So, as an example, what is the ratings that user 6 should give to movie 4? Notice that we don't have it. We have to guess it. So we have to apply one of the methods we discussed. Okay, or here, what is the rating of user 1 with respect to user 5? So we have to understand it. Okay, so as an example, the goal in this particular case is to estimate the rating for movie 1 by the user 5. And so we know that this rating is something between 1 and 5. Okay, first step, we need to apply the similarity, in this case, between the items. Okay? So we can apply the person coefficient, as we discussed before. As usual, we compute the average, we remove the average, and so those are the values that you can obtain. Okay? Should we consider all those movies as possible candidates? Notice that the set n is equal to 2, so we want to consider a neighborhood of 2 what? Items or user in this case? Items. We want to consider a set of 2 items. Which among the ones that we are considering we are going to take? The ones having the highest similarity. Okay, so I will not consider at all these and these and these. Why? Because they have they are not similar at all. There is not a correlation. Okay, while we are considering this one and that one. Notice that since we want to guess this value, okay, we have to get the value of the most similar item that has been already evaluated by the user. Okay, so we can get this and this. Okay. So, first step, I compute the similarity among the items. Then I select the n, in this particular case 2, that are most similar. Okay, now I have to guess this value, and I can apply, as you remember, either the average or the weighted average. Weighted by what? By the value that I already have. Okay? So, what I can do is that the similarity of 1.3 is 0.41, the similarity of 1.6 is 0.59, and finally, so I average, I weight the similarity by the evaluation given by the user. So this is 2 multiplied by the similarity, because it's similarity centered. This is 3 multiplied by because it's similarity centered. Okay, I normalize, and then I get 2.6. Okay? So that's our guess of the rating that the user will give to that particular movie, according to the ones that, that he has already seen. This is exactly the dual approach. And you can apply clearly it to all the other elements in the utility factor, providing that you have enough ratings on the items by the user. Okay? Questions?
So in the first step, we have to select the more similar items between the one already rated from the...
Yes, because you need, in this case, this is an item. It's not a user. Okay, so you need the items that have been already evaluated by the user in order to average them. Okay, that are similar to the one. So the idea is similar. Is this one? If I saw that movie that is similar to the ones I'm considering, and I evaluated it positively, most likely I will evaluate positively also this one. That's the idea. Okay. So in principle, those are dual approaches, and thus should provide, I would say, similar results, right? In principle, you should not expect much different results between item or user-user filtering. While actually you can observe in practice that item works much better than user-user. Why? Here the claim is items are simpler. Users have multiple tests. Okay, let's make an example. It's not difficult. Let's take myself as an example. I like very much both, I don't know, Caravaggio and Kandinsky. Okay? One is a classical painter, another one is a modern one, an abstract one. So one is figurative, Caravaggio, very famous for the use of the light, Kandinsky, very famous for very abstract shapes with colors, the theory of colors, and so on and so forth. So myself likes very completely different items. While if you take a single item, we are considering paintings, it's very difficult to say that a painting is both a classical one and an abstract one, right? While a user can like easily classical stuff and modern stuff, it's very difficult to say that an item is both classical and modern. Okay? Again, about music, I like from Metallica to Beethoven. But most likely, if you take a song, you cannot say that it's both similar to Metallica and Beethoven. This is very rare. Okay, this is the intuition why item would work better, because to some extent items are simpler, in the sense that you can apply a category and Most likely they belongs to a limited number of categories, while user can be well represented by a much bigger number of categories. Okay? Good. Now, pros and cons. Okay. The main idea here is that since we are basically evaluating items according to ratings, it works for any kind of item. I mean, you do not have to extract features. Okay, so since you do not have the feature selection as in the content-based mechanism, it always works. It works for all the items. What are the problems? Cold start. We already observed this problem. Again, you need ratings in order to make the system work. And so whenever a new product appears in the catalog, clearly you do not have ratings. And thus, in principle, you cannot apply this mechanism. Sparsity. We already observed that, again, you have maybe millions of products on Amazon or several thousands, while people like at most or give recommendation on most for hundreds. So it's a very sparse matrix. And thus, again, it's very difficult to find users that have already rated the same items, so, which is the ingredient we need for user-user collaborative filtering. Again, I cannot recommend items that are not previously rated. So you can difficultly, unless you plug some different mechanism, evaluate new items or esoteric items. And then, okay, it tends to, it tends to recommend popular items. And to some extent, it's not able to recommend items with a very unique taste, right? Because basically you are building an average profile. So while in the other case, we can capture easily even very unique tastes, in this case it's very difficult. Okay, that's why in many cases, what you can do is you can combine a number of techniques. You can put together content-based method and collaborative filtering. And we will see in the next, say, topic about latent indexing that actually you can effectively combine a number of approaches in order to get better results. But before of that, how can we evaluate the effectiveness of our system? Now we have at least, say, two techniques. One is the content-based, and one is the collaborative filtering, and the collaborative filtering with two tastes, user-user or item-item. But the question is, how can I can evaluate the performance of my system? So, given that you have a utility matrix, okay, so you have this matrix, what you can do is you can divide this matrix in two subsets. One test is the so-called training set that recall some of the technique of the machine learning. The other one is the test set. And the idea is that even if I have those numbers, so if you go back to this picture, you know that this is 3. You basically simulate the fact that you don't know that number, and you try to apply the technique in order to guess what value will give you any of the technique we have discussed. Okay? And in order to understand whether your technique has been effective or not, what you can do is you can apply the most, I would say, typical approach is to apply the root mean square error, RMSE, in which basically what you do is the following. This is the predicted value. So the value predicted for user X of item I, the value predicted for the rating of user X of item I. This is the true value that you have in the test set. And what you want to do is you want to minimize clearly the difference is an error. Why do you square this error? Because the error could be in principle positive and negative. So you want only positive value in order to have as a kind of absolute value of the error. Okay, so you square it, you make the average, and you make the square root. So basically, this gives you an idea of the overall error of the system. Where n is the number of points we are making the comparison on, namely is the size of the test set. Okay? As smaller is this root mean square error, as better is the system. The recommending system you are building. Okay, good approach. The main problem with this approach is that actually, that we will discuss also in the next slide, is that it does not take into consideration the fact that not all errors are the same. Okay. If you do a huge error on very low ratings, this is not very important. While if you do a big error on very high ratings, this is relevant because those are the items that I really would suggest to the user. So to some extent, you should consider only the top K. I don't know, precision of top 10, top whatever. Taking into consideration that even if you do big mistakes on the items that have been rated very low, that's a relatively small problem. While if you do the same mistakes, the same error on items that are rated very high, that's a big mistake because those are the items that will be possibly recommended to the user. Okay. Okay, and clearly you can apply techniques similar to the ones that we have seen in the evaluation of the search engine. Okay. The fact is that we focus on the accuracy with the RMSE. Sometimes brings some problems. As an example, prediction diversity. Well, again, we said if you saw Harry Potter 1, Harry Potter 2, and Harry Potter 3, most likely you will see Harry Potter 4. So the fact that the system will give you the recommendation of Harry Potter 4, okay, maybe will bring very high accuracy, but is really relevant? I mean, does this provide any real information? Does this open the horizon of the user to new content that otherwise he or she will not explore? Definitely not. So the idea here is that you should consider also the fact that your system will actually provide a recommendation about items that otherwise you will not consider. Okay? So you should open to prediction diversity. Another important aspect is prediction context. This is what happens when you start looking for, I don't know, a new pair of shoes, and immediately and suddenly you get thousands of recommendations about all the kind of shoes. then you actually buy the shoes you like most, and for the next 2 weeks you will still get other recommendation about shoes, even if you have already bought it. Why? Because the system is not aware of the context, on the fact that prediction depends on the context. There are instances in time where I need something, other instances in which I don't. Okay, and a good system should consider it. And finally, as already discussed, the order of prediction. It's much more important to be very accurate on high rating items rather than on low rating ones. Indeed, basically, in practice, we care only to predict high ratings. As an example, RMSE, as has been designed, as has been introduced, might penalize the method that does very well for high ratings. It's very accurate, but performs very poorly for low ratings. Okay, so we have to consider all those. All those elements. Okay, that's it. So we have now discussed the two main techniques. I remind you that we have basically this idea. We need to build an initial utility matrix, and we know how to do it implicitly or explicitly. We need to guess value, namely to extrapolate values that are not known. And now we have at least two approaches: content-based or collaborative filtering, user-user or item-item. And now we have a rough idea on how to estimate the performance of our recommending system. Next step is to put together all those elements and to see to discuss a new techniques more related to an optimization problem, to give you a rough idea on how best performer, in this particular case the recommendation system that have participated to the Netflix context. We will discuss a bit about it. At least I have an idea of how they work and what is the architecture behind those systems. Okay, so we are now talking about latent factor models. To introduce this technique, which is to some extent quite different from the ones we discussed already, we start from the Netflix price. So I guess everybody now knows what Netflix is. It's a provider of movies and similar content. The idea is that Netflix released 6 years of data from 2000 to 2005, consisting of about 1 million ratings and about 500,000 users, with 1,700 movies, it gives this data set, this huge data set, to the research community, and it retains the last few ratings for each user, about 2.8 million, asking to the community to develop a recommending system, actually capable of, as we saw, providing good evaluation in terms of root mean square error. Okay, so the idea is, I don't know, Stanford University developed a recommending system. I use this recommending system to provide ratings to the users that are not visible because they are part of the test set, and I calculate I calculated the root mean square error between the actual evaluation, and the estimation. Okay, and I submit back. I get the results, and the ones allowing to improve the Netflix system consistently, considering that at the beginning the Netflix system provided already 0.9514 RMSE, namely, this improvement would have been about 10, not about, more than 10%, got $1 million. Okay? So I think this is a very nice example of a fantastic strategy in order to improve a service, providing money to the research community. Okay? With very clear objective. This is not always the case. This works very well because the objective is very clear. I have a number, I want to improve 10%. Okay? And that's the whole idea. So from there on, clearly, a very interesting competition started, and the purpose of this last lecture is to introduce some of the main ideas behind this technology. We will not go into details, but I hope to give you the main ideas behind the developed solution. So we can, in the context of what we have already seen, basically what do we have? We have this rate with metrics made of about 500,000 users and 700,000 movies. And so what we do is that Netflix remove this test data set. Notice that is not provided to the competitors. It's simply taken by Netflix. The competitors develop a recommendation system on the basis of their training set, submit the algorithm to Netflix. Netflix run the algorithm on the test set, compute the RMSE, basically for those values, calculating the predicted rating minus the true rating, as we saw. So they know the true rating, the predicted rating is got by the algorithm, and the first able to improve the performance by 10% was the winner. Okay, that's the whole idea of the competition. Very, very interesting idea, actually. Okay, we already discussed the fact that as in most of the cases, as in most of the practical cases, the most effective technique is a combination of techniques, right? It's not only a pure one. You have to combine several techniques in order to get the best of each of them. And indeed, the Bellkor recommender system, which is the winner of this of the competition of the Netflix challenge, combine different, say, modeling of the data. The two more, I would say, extreme that to some extent we already know are the global view and the collaborative filtering. Okay, now collaborative filtering is clear. What is it? So I basically use user-user or item recommendation in order to, but you combine this with the global view. What is the global view? It's a view that does not take into consideration necessarily a specific user, okay? But it has a global view of the data. So the combination of the two approaches will provide better recommendation system. Then we have to understand what is this factorization. This is a bit more, the more technical and challenging part. We are not going again into the details. I want to give you just a rough idea. Okay, but let's put together at least at the beginning the two main the two extreme, namely global recommendation and collaborative filtering. And let's see what are the improvements simply applying those two techniques. Okay, what is the global recommendation and what is the local effect? Okay, the idea is the following. Okay, you can know that globally the average rating of a movie is 3.7. Okay, so basically, considering the system that is usually provide ratings between 1 and 5, what we are saying is that most of the people provides a mild positive recommendation to a movie. Okay? Good. This is global because it's the average among all the ratings. It's not by user. Okay. Now you know that the sixth sense, the evaluation of the sixth sense by all the users is, the sixth sense is a movie, is 0.5 stars above their average. Okay? So 3.7 plus 0.5 gives you a rough idea of what could be the evaluation of the sixth sense. But then you know that, look, if you consider a particular user, Joe in this case, usually it gives recommendations that are 0.2 stars below the average. Okay? Combining all this information, okay, you will get that the average is 3.7. The sixth sense in average is evaluated 0.5 plus the average. But Joe is a very tough evaluator that usually gives 0.2 below the average. Okay? Okay. So basically you will get this 4 that gives you a rough idea of what would be the evaluation of Joe of the sixth sense. Okay? So basically we are now filling up our utility matrix observing global variable. The average value for a movie, the average value by a user, and that's it. You combine all the stuff and you get this baseline. Okay, but then you can add information to this. And thanks to collaborative filtering, you can know that Joe didn't like movies that are considered similar to the sixth sense. Okay? And so plugging in, this is the sign that is a movie that is considered similar to the sixth sense. And so plugging this information, this further information, basically you can estimate that instead of 4, because of the fact that Joe didn't like that movie, you are subtracting another factor 0.2 and you get 3.8. One possible evaluation of the rating that will possibly Joe gives to the sixth sense. Okay, now we know everything about the collaborative filtering. So this is something that we already saw, and the estimation of user X of item I is given by the weighted estimation of X of products that are similar, okay, to I. Okay, this is the item, what we called before item-item collaborative filtering. Good. Nothing new here. Okay, so what we can do, we can put together all these ingredients. And so we have the baseline that which is made by the average of the ratings, by the average of the user, by the average of the item, okay, plus what we saw before was the minus 0.2 because it doesn't like, Joe doesn't like the sign that is a similar, plus the contribution of the collaborative filtering part. Okay? So we obtain a kind of hybrid model, putting together a baseline global view together with the collaborative filtering part. Nothing particularly new. Okay, you can make some optimization instead of considering Sij, considering some weight, but nothing that changes the main concept here. Okay. So what we want to do is we want to make a good recommendation, and we know that um, making good recommendation means that the RMSE is as low as possible. Okay. In principle, what we want to do is we want to make a recommendation on items that the user have never seen, right? That's the main purpose. But at the same time, we are not oracles. I mean, we cannot predict the future. So as a proxy to estimate the future, we have the test set, which help us to get to estimate value that we don't see but are available to the system. Okay? So the idea is let's make a system that is capable of predicting in the most effective way something that I know, but I forget to know in order to evaluate the performance of my system, namely the testing set. And let's hope that this system will know very well also on system that on items for which I don't know actually the rating. Okay, that's the main idea. Okay. Simply, I remind you that Netflix, at the beginning of the challenge, had a recommendation system providing a root mean square error of 0.95. Simply plugging basic collaborative filtering and this idea of local and global, already you get 0.94. So you have an improvement of 1%. Okay? So simply employing techniques we saw, we got to 0.95%, and okay, considering other techniques, you can get to 0.91. So a step towards. But in order to win the prize, we need something that is 0.85, because we need to improve the system by 10%. Okay? So the question is, how can we get this improvement of 10%? What are the techniques to get this 10%? Okay, and this is the idea of latent factor model. Okay, this is a kind of magic, if you want, that you already saw when we made the exercise exploiting DBpedia data. We basically, in order to show that the classes of painters and musicians were actually distinct, we reduced the dimension to 2. Okay? We started from the huge dimension of 1,000 of terms, and we reduced the dimension to 2, just simply to show that the two classes were actually pretty distinguishable. Okay? So this is a technique to reduce the dimension. Okay? So the idea is, to what extent we can, taking the original matrix, the original utility matrix, we can basically reduce the dimension of the user space, of the item space, and reduce the dimension of the user space, in this particular case to 3, but in general to k. Okay, so to what extent we can find two matrices, P, transpose, and Q, where Q is a metric that reduces the space of the user, while P is a matrix that reduces the space of the, of Q is the matrix that reduces the space of the user, of the factors, of the items, sorry, so that multiplying the two matrices, I roughly get the original R. Okay? Now, from an algebraic point of view, it works. There are no reasons why it should not work, right? Basically, I'm writing a matrix as the product. I am a M by N matrix, and I do m by k multiplied by k by n. That's it. I will get for sure something that is m by n. I don't know how to reconstruct it, but it should work. Why not? What is the trick here? The trick here is that if I consider a particular item now is not anymore in the space of millions, or I don't remember now, 500,000 of users, but in principle could be on k factors. What is the meaning of those factors is not yet clear, because we have then to attribute a kind of meaning to those factors, and it can be not so easy. But we will see that those items, namely the movies in this particular case, the factor will represent some kind of genre of the movies. Okay? Similarly, users are now not anymore represented in a very huge space of items, namely of the movies, but in a three-dimensional space in this particular case. Okay? This is the main idea. So let's assume, let's pretend, and actually at least, I mean, on the paper it's possible that we can write R as the product of an item by factor 3 in this particular case, matrix Q, multiplied by a user that is user by factor, in this case again 3, P transpose. That's it. Okay? Now, the idea is the following. If you take this three-dimensional space, and now for the sake of simplicity, assume that instead of a three-dimensional space, you have a b-dimensional space. Okay, those factors can be related as an example to the fact that the movie is funny or serious. Okay, attribute a meaning to the factor can be not trivial, but there is some latent meaning. Okay, so basically we are reducing the dimension in the hope that the meaning, the overall content of the information is maintained in a smaller space. What is the meaning of this smaller space? As an example, in this picture, you have funny movies and serious movies, or you have movies that are more appreciated by female, or movies that are appreciated more by females. Now, if you have this reduced space, each item, each movie is a point in this space. And each user is a point in this space, right? Each item is a point with 3 dimensions or 2 dimensions, as in the case before, in that space. Each user is a point in that space, right? And so the idea is that now we can basically have the movies and the users that are placed on the space according to their representation in that that space with the reduced dimensionality. And clearly, again, you can say that user and movies that are close by most likely are user and movies that are related. Okay, that's the whole idea. Why is this idea interesting? Because now, how can you evaluate the value of a rating that you didn't see? Okay, simply, if you want to evaluate this value that you don't know, having those two matrices, Q and P, what you have to do is simply to multiply QIF by PXF. So in this particular case, the item and the user, you are taking the second item, so this, and you are taking the 1, 2, 3, 4, 5th user, 1, 2, 3, 4, 5th user. Simply multiplying this by this, you will get an estimate of that, according to the definition. Clearly here the hope is, as we said, that given that P and Q have been defined and computed trying to minimize the root mean square error of the known values, the hope is that they will also minimize the error on unknown value. Makes this sense to everybody? Okay. So we have an original utility matrix, sparse, very big. We find the representation as the product of two matrices in a reduced space, k dimension, okay, such that the multiplication of those two matrices will give the original matrix. Now it's easy how to compute unknown values, and the hope is that obtaining a good representation, a good, a product of the true matrix P and Q that where we present a known value, that will well reconstruct known value, namely minimize the error, you will possibly also get a good reconstruction of the unknown ones. Okay, so the question now is how to compute P and Q. The intuition is to some extent clear. But now, how can we reconstruct P and Q? Okay, so you see, this is what we want. It's the second item of the fifth user. We simply multiply the two, and we get 2.4, and so our estimation is 2.4. Okay? So now we have the movies in this space. We have the user in this space, and hopefully users and movies that are grouped together are the ones that have some kind of relationship. Okay. Good. How to find out this representation of P and Q? Okay, what we want to do is very simple. We want to minimize the error. The error between what? Between the real value, the square error, between the real value and the guessed one. I remind you that Qy multiplied by Px is the guessed value, is the reconstructed value, is exactly this, right? Qi by Px, okay? So basically, we are simply applying this. And what we want to do is we want to minimize the error. Okay, that's it. Okay. So the idea is the following: we want to minimize the error, but at the same time, up to now, we considered k given, namely the number of factors that we consider, right? Now the question is the following: clearly, you have two extremes. On one side, you would like to have as much factors as possible in order to have a very rich and complex model. On the other side, the risk is the following. If you have a very rich and complex model, the risk is that the model will adapt to the training set. You will have the so-called overfitting. So you have to trade off between those two needs. Even in the consideration that clearly what you want to do is you have k as big as possible in order to, to have a latent model that well capture of the signals that are inside the information. But at the same time, if it is too large, it not only captures signals, but it will also encapsulate the noise, and so basically you will not generalize. So we have to consider those two things. Also in the consideration that the error, the SSE, the square error, will start increasing as soon as k is bigger than 2. Okay? So it seems there is a kind of correlation between the error of and begin to rise as soon as k is at least 2 dimension. If it's too big, clearly the risk is overfitting. If too small, k is too short, basically you are not capturing the model. Okay? So we need to trade off those 2 components. And so what we can do is that we want, this is our original function. We want a function that is accurate, but at the same time, we want a function that is not too much complex. So we have here a weight. This is the size of the factors, right? So this takes into consideration the complexity that you will have in your model. So you want to minimize both the error, but at the same time also the complexity. Okay? This is the idea that you have here. Why? Because if you don't take into consideration this element, there is a very high risk of overfitting. Due also to the fact that, don't forget, that the matrix is very sparse. Okay, so basically there are a region of the matrix in which you miss a lot of information. And so if you apply the model to that region, most likely you will get overfitting. I mean, you are adapting the model that has been built on this contribution to regions in which you do not have information. Okay? So you want to trade off between the 2. Clearly, if lambda is 0 here, you have a very good model, very complex model, but with high overfitting. If lambda is very big here, you have a model that is trivial, no overfitting, but basically you don't have a model. You don't capture the knowledge in the data. Okay, so we need to optimize this stuff. This is a quadratic function. So quadratic function means that even if you don't know exactly what we are talking about, you can apply, you can minimize the function with gradient descent, basically. Okay, so what you do is, this is our function, it's a quadratic function. Okay, we start from a given point. Okay, we compute the derivative. On that derivative, we take a step. The step is, the learning step is uniform. And so we move here. What are we looking for here? Sorry? The minimum. So we have to reach this point. We have to compute this point. We start from any given point. What we need is a way to reach this minimum. Okay? So what we do, we compute the derivative, we move here. Then we compute the derivative, now it's here, we move here. Once the derivative is basically 0, we are not moving anymore, right? Because the size of the step depends on the slope and thus depend on the derivative. That's it. So basically, we are very aggressive here. We descend very rapidly here. As soon as the derivative becomes almost 0, we relax and we have a very tiny increment in order to compute whether we are moving toward the optimum or not. That's it. Okay? But if this is true, we can apply it to this. It's a quadratic function. There are no reason that we cannot apply this. Okay? And so basically what we can do, again, is we rewrite the same stuff, and simply we consider that the derivative of p, so p at the time t plus 1 is p at the time t minus, this is the size of the step that we do, the learning parameter, multiplied by the descent, the slope. Okay, the slope, since it's quadratic, is very trivial. I mean, you can compute it algebraically in a very convenient and easy way. Okay? Okay. Computing the gradient is slow, so you can use an advanced technique in order to improve the performance, and in particular, you can use a stochastic gradient descent. Okay, those are optimization. Very important optimization, right? Because they do not change the main concept, the main idea behind this approach, but anyway, they make the differences. They make the difference. I mean, you have to apply efficient techniques. Anyway, the fact is that we can find the minimum. Okay, so we have now a technique to compute P and Q. And once we have P and Q that minimize the root mean square error, we can guess the other value in the hope that this guess is well supported by the evidences in the practice. That's the whole idea. Okay. Okay. What is nice here is that you see that indeed you have grouped together by factor vector 1 and factor vector 2 that are two example movies that likely are related. Okay, you have bloody movies in some area and you have romantic movies in some other areas. So indeed, this idea of applying a latent mechanism in order to find out the hidden signals in the information is well captured by this picture. Oops, okay. Okay. This is everything together. Okay. The mean average, the contribution of the user, the contribution of the movie, and the collaborative and the user-movie interaction by the latent factor. What is interesting here is that if you put together all this stuff, something that we didn't see, but again, it's important, but it's not crucial to understand the main mechanism, you get to 0.89. Okay? You get a significant improvement of the performance. Then another message, relevant message, is that in order to achieve good results, you have also to consider the fact that ratings changes over time. And so basically what you can do is you can introduce this concept of time into the evaluation. And again, if you put together also time, you are very close to our goal. Okay, the fact is that somebody actually got the prize, and those guys, and it's a very nice example on how investing on science can make also the difference in practical terms. Okay? Questions? Okay, see you on Wednesday. Thank you.